Hi, my name is Morgan Bertrand, and today I'm going to explain tangent and velocity. Let's start off with some review. First of all, a secant line is a line that intersects a curve at 2 points. This line represents the slope between the 2 points, which can be seen in the two examples. Similarly, a tangent line is a line that touches a curve at only 1 point and does not intersect the function at that point. This line also represents slope. However, a tangent represents the slope at one specific point on the graph instead of the slope between 2 points. In this first example, you can see a secant line and a tangent line graphed on the same function. Notice the secant line with 2 intersection points and the tangent line that touches the graph at 1 point. Here is another example of a tangent line. Now be careful not to get this example confused with a secant line. Although it touches the original function at 2 points, it does not intersect at both. A tangent line can intersect a function at multiple points, but the important part is that it only touches the curve at the point whose slope it represents. This next graph also shows the 2 tangent lines that touch points on the curve of this sine graph. Now imagine that this blue curve continues on forever. The top horizontal tangent line would touch at infinite number of points on this graph, which means that these infinite points all have the same slope, in this case the slope being 0. Now, to build on what we just went over, the approximate slope of a tangent line can be estimated using secant lines. Let's quickly review point slope form. Point slope form is written as y minus y1 is equal to m times x minus x1. To break this down, x1, y1 will be the point that is shared between the function and the tangent line. The variable m represents the slope, and therefore the calculated slope of the tangent line will be substituted in for m in the equation. The problem with calculating the slope of a tangent line is that we only know one point on the line, and that is the point shared with the original function. Yet 2 points are needed to calculate slope. To solve this, we will use another point on the function with x values that are close to the known point from both sides. Another way to state this is that we are finding the limit. The slope of a tangent line is sometimes referred to as the limit of the slopes of the secant line. This can be stated as the limit as point Q approaches point P of the slope of PQ is equal to the slope of the tangent. Let's try an example. Y equals x squared is graphed in the blue on the left. We want to find the slope of the red tangent line that touches the point 2, 4. To calculate the most accurate slope, we want to find the y values for multiple x values that are really close to x equals 2 on both sides. After we find these points, we will then calculate the slopes between each new point and the main point 2, 4. To save time, I went ahead and calculated all these values and organized them into an easy chart. If you take a look at the m column, you will see that all of the slopes appear to be approaching 4. Therefore, this is the slope of our tangent line. To finish, we must plug our values into the point slope form equation. Our final answer is then y minus 4 equals 4 times x minus 2. You can see that we got this by plugging in the point 2, 4 into the equation and then plugging in the slope 4. Another way to find the slope of a tangent line is to use data and a graph. Sometimes a problem won't give you a function and instead gives a chart full of data. You will need to start these problems by graphing the data points onto a graph. Then sketch a curve to connect the points, which will give you a rough estimate of the graph and all the points. Let's take a look at this example. In the chart on the right, there are 7 random data points that were given to you. I started by graphing the points and connecting them with a curve, as seen on the graph on the right. Next, you need to draw a tangent line to whatever point the problem is referring to. In this case, we will have a tangent line touch the curve at about the point 1/2, 0.78. After you draw your tangent line, you need to make it into a triangle with the tangent line as the hypotenuse. Then use the graph to approximate the points on either end of the hypotenuse. These will be the points that you plug into the slope equation. For this example, the 2 points that I estimated were 0.35, 0.6 and 0.6, 0.87. If I go and plug these 2 points into the slope equation, which is y2 minus y1 over x2 minus x1, I get a slope of about 1.08. Again, we have to then plug into point slope form, and we get our answer of y minus 0.78 is equal to 1.08 times x minus 0.5. Now that we know all about tangent lines, we can apply this to velocity. Velocity is the speed of an object in a certain direction. The average velocity, which is the change in position over time, can be found by using the slope of a secant line. The graph below is a simple example of the average velocity between point P and Q, represented by a secant line. Instantaneous velocity is the velocity of an object at a specific time. This is the same as finding the slope of the tangent line and uses the same process of finding the tangent slope with secant lines. In other words, you simply find the average velocity for small intervals of time that are approaching the designated time. Let's try a quick example with velocity. In this problem, the distance in meters that an object travels over in t seconds is represented by d equals 3s squared plus 2. Find the instantaneous velocity at 2 seconds. To solve this problem, we will take the same approach as any other tangent and secant problem. We will plug in x values that approach 2 from both sides into the equation and use these points to calculate the slope of the secant lines, or in this case, the average velocities. Once we complete these calculations, it is obvious that the average velocities are approaching a velocity of 12 at 2 seconds. Therefore, the instantaneous velocity at 2 seconds is 12 meters per second. That is all for tangent and velocity. Thanks for watching.